We'll talk about some results for hard rods of inhomogeneous size.
So first of all, I would like to thank the organizers and Makiko for inviting me. Even if I'm not from the BBS family, it's always nice to learn new things. And in fact, this is also the reason why I would like to thank Pablo, who let me join this project of our rods. So this project started in, I think it was 2019 when Herbert visited Buenos Aires. And at the time, Dante was the student of Pablo. And then last year, together with Pablo and Herbert, we were in Messera in Berkeley, and that's where I joined the project and I discovered the hard rods world. Okay, so my plan for the next 45 minutes, would be to introduce the model of inhomogeneous rod and then to establish some connection with the free gas dynamics and the Poisson line processes. And then I will give some hydrodynamics scaling limit results, and we'll see that we describe the microscopic evolution. So what is a hard rod system? So a hard rod is a sort of elongated particle described mathematically by a three-dimensional point, where y is the position, v is the speed of the rod, and also has some length r, which for this talk will be a positive real number, but in principle could be extended to negative length. So you see that the state space is either R3 or R2 Cartesian R+. And a configuration, so I denote Y, a configuration of rod. And the state of configuration is such that rods do not intersect, and this is why the word hard means. And also we have a finite number of rods. Okay, so then you ask, okay, what do these rods do? They when time evolves, so they evolve deterministically. And if you have just one rod, the position is just at time t is just v times t. But then if you have more rods, at some point they will collide, and then you have to give the collision rule. And so they collide when the end point of the first rod touch the first point of the second rod. So when this condition is satisfied, the y2 equal to y1 plus r1. And what they do, they just swap their position, and then they keep their motion as it was. And I think it's easier to have a picture to describe what's going on. So for me here, time doesn't go down, goes left, right. Y is the initial configuration of these two rods, the purple one and the pink one. And then you see this is T minus. So T minus, they touch each other, they swap position, and they continue their motion with the speed that was assigned at the beginning. Okay, so this is a model. So inhomogeneous size means they have different length. And before going any further, let me give you a bit of bibliography. So they were initially studied between the 60s and 70s. Jepsen studied some space-time correlation, and then Sinai, Eisenman, Goldstein, and Lebowitz, they studied ergodicity property. And finally, in '82, there was this paper of Boldrighini, Dobrushin, and Sukhov, where they studied the hydrodynamic limit for a system of homogeneous rods. So here, the idea is that we generalize the mass, the size of the rods to different lengths, while for them it was the same length. And then there is a section of rods in the book of Spon. In '97, Boldrighini and Sukhov proved the fluctuation around the hydrodynamic. And then recently, Doyon, Yoshimura, and Co, they showed that more, they showed the generalized hydrodynamic that is satisfied by the soliton gas, of which the hard rods is a sort of, they have a similar macroscopic behavior. Okay, so this was the first part. So it's clear the dynamics of the rod system. So now let's go to the second item. So the ideal gas evolution. So very similar of the rods. Now an ideal particle of gas is again a two-dimensional point. X is the position, this is the velocity, and now R, you have to think of R as a as a mark, can be so positive or negative. And this mark is something you attach to the particle. So in fact, it's a two-dimensional object. And you see in the evolution of the free gas, the mark doesn't play any role, unlike the rods. So it's just they travel ballistically, ignoring each other. So this is what's going on. And the time evolution is described by this capital TT operator. Okay, so this is the free gas dynamics. And then it's worth to introduce this high function associated to the configuration X. So I use X for the configuration of the free gas. Okay, so this high function is in the spirit very similar to the high function of exclusion process. I study particle systems, so for me it's natural to make this connection. And you see, it basically gives you the number of net lines crossing the point 0, 0 and xv in the plane xv for fixed time. For example, at time 0, if this is the initial configuration of the rods, you see this is an inhomogeneous jump process where the jump is precisely the length of the rods. So for every fixed time, you have something like this, which is non-decreasing if you have if you only allow a positive rod size. Okay, this function h, then from this a function, you can define the length flow and the mass of the configuration x. So the length flow again is this difference of high function at time t and 0. The mass of the configuration x is the sum of all the marks of the ideal gas. And the sign mass is the mass between the sign mass of the configuration X between point A and B is the mass between point A and B. You can define the net flow also using the mass, because if you think about it, you can write the net flow in the following way. So the mass of the particle of the lines with velocity less than v minus those with velocity bigger than v. So again, I think a picture it's useful. So you see J in this picture is the positive contribution of the purple and blue line, whose velocity is less than the one of the black line, minus the contribution of the mark of the green line, whose velocity is bigger than the one on the black line. And again, we will consider configuration of X with finite mass flow, this curly X. Then you may wonder how to connect the free gas dynamics with the hard rod dynamics. And this was already in the paper that I mentioned of Boldrighini, Dobrushin and Sukhov, where they introduced this dilation map and contraction map. So the dilation map goes from the free gas world into the hard rods world, and you see, so it's always defined with respect to a point, which for me it's this point A. So I have, in my next slide, I have the math, but I think again, a picture, it's easier. So you see you take straight line around the 2 points next to A, and then you dilate, accordingly to the mark of the particle. And then similarly, when you have, for example, the blue gas, so you have this line, which is parallel to this one, and then you dilate again, and so on. So this is how you go from X to dAx. And similarly, you can go from the hard rods space to the free gas in the following way. You shrink, you contract them up. And these two lines are straight, and these two lines are straight, and so on. So the description is the following. So the dilation maps goes from the curly X to the curly Y, which was the space of hard rods configuration not contained in the point A, because you have to dilate with respect to a point that doesn't belongs to a rod. And you add the mass of the point X. The dilation of the point X is X plus the mass between A and that point. And similarly, the contraction, which goes from the hard rod set to the free gas set, is the Y minus the mass, which is between A, the point A, with respect you are shrinking, and the point Y. Okay, so this is a way to go from the free gas to the hard rods. And this is useful because then you can describe the hard rods evolution in terms of the free gas evolution. So one way to do that is that you define, you describe the position of a hard rod, which I called Y, in terms of the associated ideal gas particle, X dt. And this is precisely the dilation of the point X plus the bare speed. And you have to take into account the flow, so the number of net lines which have crossed your original line. And so at time t, I denote uty, the configuration of the rods at time t, which is precisely given by the position y, same velocity, same length of the rod. Similarly, you can define again in another way the evolution of the hard rod's configuration y in the following way, following the position of a tag rod. So here you see again, you have that u, so the position of the rod, which initially was in y at time t equal to 0 with final length, is what? It's this free dynamic y plus vt plus the contribution of all the rods which has for which you had a collision. So in this case, y t y is the one that is written at the end of the slide. Okay, and you see that so you have to adjust. Okay, yes, you have to take into consideration all the lines that cross the path you are interested in following. So this is the main point. Finally, using the dilation and contraction map, you can also describe the evolution of the configuration y. How do you do that? So you start with y times 0. You contract, so you go to the free gas. You let the free gas evolution evolve. You have the straight lines. You dilate your free gas particles, so you go back to the hard rod. And then you, if you think about it, you have to shift the configuration because again, there are, so every time a line crosses the horizontal axis, then there is a shift you have to take into account, and you have to compensate that with the shift operator. So you shift by an amount, which is the position of an initial rod, which starts at the origin with 0 length, 0 velocity. So I think again a picture is it's clear. So here I have, so on the left hand side you have to compare the. So we start. So with the initial rule that I gave, this is y. I have 3 rods, they collide, I swap position, and then I let them evolve. So I have this one. But if I want to go to the free gas world, what do I do? So I start with y. So this is exactly the same of this one. I shrink my configuration with respect to the origin. I let the free gas evolution. Again, I dilate with d0. And then I have, since these lines across the origin, I have to shift a bit by this amount. Okay, it's basically plus this minus this. Oops, it's okay. If you think about it, this is what is going on. Yes.
The origin was very far. I mean, how
what do you? Sorry, what do you mean very far? In which sense? This blue line. Okay. So you wouldn't have to do the shift if there were no line crossing it. If, as long as there's a line crossing it, you do some shift. Otherwise, no. Yeah, you don't.
You can put it very, very far.
Yes. Yes. Exactly. Yeah. Exactly. Okay. So up to here, everything was inspired by this paper that I said of Boldrighini, Dobrushin and Sukhov, where these maps were already defined. But now this is a different perspective, different perspective of looking at the hard rod system. So now let me introduce Poisson line processes in the following way. So there is a one-to-one correspondence between points of the XV plane and the so-called ballistic line in the other picture. So you see almost one-to-one bijection, because you cannot describe vertical lines, those which have infinite velocity. So for example, here you have this red point correspond to this line. So this is the same height in the vertical axis, and it has negative length. The pink one again has negative length, and it crosses the vertical axis precisely at this height. And similarly for the blue one and the green one, they have positive length, and they cross the vertical axis at the height of that is given in this picture. Okay, so now we have a so-called like a marked line on the right picture. Again, I did not use the mark R, but you have to think that each of these lines has a mark attached. Okay, so now for each segment, AB-oriented segment, which is the linear interpolation of the points, two-dimensional points A and B, you consider, you want to define the set of lines intersecting this segment. And you want to split this set into those lines that intersect from left to right. So if you are here, left to right would be this one. So for which the velocity is smaller than the one of the segment. And so the one of the segment is just the slope. Or those crossing the segment from left to right, from right to left, like the blue one. So if you're in A, you see the line is going from right to left. Meaning the velocity of the blue line is bigger than the one of the segment. Okay. And so now some notation. So I said that you can always interpret this free particle as a marked line XV. And then, so now we need to have, so we asked for a measure, space locally finite measure on R3 with the Borel sigma algebra. And then X will be a Poisson process, which has this measure. And we ask for a density. So the density of the measure is F, which is the intensity of the Poisson process. So that the mu of Borel set A is given by this triple integral. And then, due to the mapping theorem for Poisson processes, the map PT applied to the Poisson process is again a Poisson process, which an intensity that is given by mu for the inverse of the map that we would just be having time backward. And we will use for the scaling limit result, we will use rescaled Poisson process, which with intensity, with the rescaled intensity epsilon minus 1 F. Okay, so the first, again, the first object we define in this in the space X is the so-called chance of the Lantijou field induced by the marked line. So what do you do? So imagine you have the two-dimensional plane XT. Each line that you draw divide the plane into half space, and you give high 0 to the half space containing the origin, and high either plus or minus R, depending if your line is crossing the vertical axis above or below 0. And you can do this with a finite number of lines. So if it was just one, so let's ignore the orange line. So just look at the blue line. I give high 0 to the half space containing the origin and plus R to the other half. If I have the contribution of the orange one, I have this space. Now I have the plane, my space is divided in 4 sections. This section has high 0. This is high R. This is high minus R, because the orange line crosses the origin in the negative part of the vertical axis. And this is the contribution of the two. So R, blue R minus orange R. And if I sum, so if I sum all over this contribution, I have this object, the chance of Lantijou field, this HA, which takes into account all the contribution of this marked line. And also, so I think this picture is very informative of what is going on. So you see that on the right-hand side, on the left-hand side, you have the free gas dynamics. So you have these straight lines with the initial configuration X, which evolve according to this operator TT, which is X plus VT. And you can interpret the other picture in two different ways. So one is the hard rod exchange. So you see you have 3 rods of length of color orange, red and orange, or green. And they swap and they continue. This is the configuration at time t. Or you can interpret this picture as a 3-dimensional picture, where so the length of the rod is the height of these steps, of these terraces. So this is a 3-dimensional picture of different levels. So this step is at level 0. Then you go below of minus orange R, you go above, and so on. And so this is the highest one, which is high red R plus green R. So in a 3-dimensional picture, these are stairs, which is exactly the chance of Lantejoule field. Okay, and so now let's go to the scaling limit. So now you have this H. You define the rescaled chance of Lantejoule field, where you sum not on the point of the over the point of the rescaled Poisson process, and you multiply by epsilon. And then you basically have a lower large number for this object. So you let epsilon go into 0. I didn't prove too many details of the proof. I didn't put too many details of the proof. The idea is that you can write your rescaled Poisson process x epsilon as the union of epsilon minus 1 independent Poisson process, and then you basically use the lower large number for Poisson process. Campbell's theorem gives you the expectation of the ith object of this sum of epsilon minus 1 element, which is precisely this triple integral of R times the lines. So R times the indicator of the lines crossing the segment OA from left to right or right to left, don't remember, times your mu. And if you call your mu, your R times mu, you define another measure, mu1, this is precisely mu1 OA bar minus. And you do the same for OA bar plus, so the number of lines intersecting the segment in the other direction. So you have the lower large number, then you also have central limit theorem. So again, here you have to rescale according to the central limit theorem scale. You take your object H epsilon, you subtract the mean, you rescale by square root of epsilon, and then the limit as this going to 0 of this object is the so-called Levichenson field associated with some distance mu2, which is defined in terms of a white noise, for which the control distance is exactly mu2. So you have, so W or A bar is the white noise, meaning that the W of a Borel set is a random variable distributed with a normal distribution of mean 0 and variance, which is given by the control measure of the white noise. And you can also define the covariances. And again, Campbell's theorem gives you the variances of the eta. Okay, so this was lower large number and central limit theorem for this H field. But now what we are interested is the empirical measure associated to the Harrod's process. So we define an empirical measure as K epsilon T associated to a test function. Again, here we are rescaled, and now we are not in X, we are in the Y, in the Y space, in the Harrod space. So so here Y epsilon is the space of Harrods which have shrink length epsilon R instead of R, and the density is epsilon minus 1, so that the global mass is still of order 1. And then the hydrodynamics limit tells you that if at time 0 this object converges to something, which is this measure whose density is this G, Y, VR, then you want to prove that at time t, you have a similar convergence with respect to a measure which has some density, GT, which you want to be characterized. And the way to characterize this is to have some Cauchy problem for which the GT, the density, is solution. Okay, so again, the proof is to go, instead of to the y epsilon word, to bring to the free gas x epsilon word, because then you can take advantage of the fact that x epsilon is a Poisson process, and then you use the results before for the chance of Lantejoule field. Okay, you have to perform a change of variable, and eventually you get what you expect. So how to characterize the macroscopic evolution of the Harrod density? So this GT. So this is given by the hydrodynamic equation, which is this transport equation, where the transpose coefficient is this effective velocity, which has this form that I will discuss in a second. So you have the time derivative of GT plus the y derivative of GT times this transport term, which has an explicit form. And you see at time z, the initial condition at time 0 is precisely the G of the hydrodynamic limit at time 0. Okay, so to prove this macroscopically, you need to define the macroscopic counterpart of the operator that I described at the very beginning, this dilation and contraction map, the free time evolution, and the shift operator. So they are defined in the following way. So for a function f, the mass and the momentum function are given there. It's the double integral of r times f and double the integral of vr times f, respectively. And then the dilation is of a point B with respect to a point A is precisely the B plus the mass you have between the point A and B. Similarly, the contraction map. And then the shift, again, is a similar form. And so the free time evolution as before. And given this operator, you can, precisely as we did before, you can describe the GT. So the GT is your evolution curly UT applied to the initial G, which is given, can be given in terms of this operator. So you contract, you have the free time evolution, you delay it, and then you shift. But an alternative formulation for this GT is given in terms of the initial G in the following way. And this is, in fact, the one that you use to describe to find the PDE that satisfies the GT. Okay. So I will not prove the fact that these two are, you can go from one formulation to the other one. So the idea is that you use some auxiliary results, which are the derivative of this UT. If you remember, UT was the position of your rod, which initially was at time y. So it's y plus VT. So the contribution of the rod plus the contribution of the collision with the other. So you take some derivative of the inverse. See that, maybe just to give some intuition, see that, so for example, this term will produce the contraction because it's precisely this term of the formula. And similarly, the other one will produce the dilation. The 1 plus sigma is here. This is the time shift. So, okay, maybe it's easier if you just believe me. It's a bunch of computation. And this is what you have. Okay. Similarly for the how do you get to the hydrodynamic equation? So you use the alternative formulation of the GT, which the one given with the initial function G. So you take this one. So we want to take the y derivative of this right hand side. And again, you use the t derivative. You use some auxiliary results that you can prove. So this is just the derivative of the product. I have this. I substitute the color with the corresponding color. And then I just, so here I just rearrange things accordingly. And eventually I get to here. And this is what I call my effective velocity. And to have some intuition on the effective velocity, you see it's the contribution of the bare speed, v, plus the contribution of the colliding rods with speed w. Okay, so this is the hydrodynamic. And then another thing that you might ask would be some low large numbers, some hydrodynamic results for the position of the tag rod, which is initially placed at the point Y. So you have and you want to follow the dynamics. Again, you rescale U, you go to the configuration Y epsilon. And then as epsilon going to 0, this object converge to something, which is again solution of a PD. So in particular, so the time derivative, as you expect, the time derivative of the tag rod is the velocity, the effective velocity of the rod. The initial condition is the position of the rod at time 0. Again, here to see this, basically you consider the red. So you see that this red on the right-hand side of the red identity quality, it's basically the effective velocity. So you just want to prove that the left-hand side is the time derivative of u, which again you can do performing a change of variables. So this is how you get this PD. Okay, and then this effective velocity, using the fact that you can write it in terms of the mass and momentum of the GT. So you can write it in this way. So the denominator, so if you remember the psi and the sigma here, okay, so this is sigma, which is 1 minus the denominator, and this is psi. This is, so the red one is minus the effective velocity. So you have here 1 minus sigma, and above you can write 1 minus the psi. So eventually you have this form of the effective velocity, and you see that if you subtract the effective velocity for V and W, you get this simple term, which you can plug in again in the definition of the effective velocity that I gave you when I show you the Cauchy problem for the GT. And eventually, so you get this, that the effective velocity satisfies this implicit equation, implicit because you also have effective inside the integral. And now I wrote it this way because phi is the collision rule. In what I understood in this business is that different systems have different collision rules. So in particular for the hard rods, phi is a simple in the sense it's just the plus or minus the length of the rod. There are models for which the collision rule is more complicated, like the soliton gases, phi in terms of some logarithm function. Okay, so this is the last result. And okay, then of course there are open questions. So negative rod length, I think mathematically can be done, but physically I'm not sure what does it mean. And then since I work with particle systems, it's very natural to have stochastic rules when the dynamics evolve. So not to have so here the randomness is just at the beginning of the initial condition. But in particle system, each step there is some randomness. And one way to add this to the system is that instead, so when you have two rods colliding, instead of swapping the position, you condition it on having the total length of the two rods fixed, preserved, and then you put some fraction on the first rod and some other fraction on the other rod. And this fraction is distributed according to some random distribution. So this is inspired of the work of Kipnis, Marchiori, and Presutti of 82, where they have exactly similar redistribution rule for particles. So instead of the length, they have energy. So they have particle exchanging energy in this stochastic way. And then I think particle with you can give particle acceleration. So instead of straight line, you have some curve that you can interpret from as external forces. I think this was Herbert's question. Of course, large deviation is always a question. And finally, BBS enter in my talk. Can you do something similar for BBS? And then also I would like to understand these other models, which seems to have similar framework, but I don't know if there is a deep reason for this happen, or it's just turned out to be this way. This would be interesting to understand. So if in some sense they belong to some to the same, I don't know, I don't want to say universality class, but this kind of question that now are very popular. Okay, so I'm done. Thank you for the attention. No, we can share.
Yeah, thank you very much. So I actually for box-ball system, I will talk tomorrow about some result quite related to your talk. And but the box-ball system case, the difficulty comes from the position of origin. So as you said, you have to give some shift for this blue line. But for your case, it's not so difficult to compute how we need to shift somehow. Well, it's hard, so it's complicated. It's simple. Yeah, BBS is also deterministic, but okay. Yeah, yeah. Once we understand this origin problem, it's almost the same thing holds. But so far we can only do that at the beginning only particles exist for half line. Or yeah, so but. Yeah, so your case is any initial configuration is okay. But so with finite numbers means so for hydrodynamic limits, since you will take some limit convergence with some density, so you increase the number of rows, and so okay. So then if we want to understand the stationary case, then we need infinitely many rows, I think, and with seen or study such case. Maybe one more question is, so your case is inhomogeneity of the size of R is, I think, the point. And so how this affects to your study? Essentially same. So no new difficulty, or so technically, no. Okay, I see.
Other questions? Yeah, can I ask a question about this formula? So my understanding then is that your particles, they are characterized by a velocity and a length, essentially. And then when they collide, well, there is a shift that depends on the length. And so then you have a density G, a function of position, velocity, and length, and all that. But why you don't have an effective velocity that has an R parameter in it as well? That's what I don't fully understand. So I would have expected if I just use our GHG formula kind of trivially, naively, and write these formulas, I would have a VF that also depends on R, because I would look at the effective velocity for the particles that have that length and that velocity. So the question is, suppose I take out these GHG formula, does it come back to that? I mean, it simplifies for some reason, and then you can define an effective velocity that does not depend on the R, and that satisfies all of this.
No, so I don't have a good answer why does not directly depends on the R. It's true. I mean, it's true that the dynamics it so depends on the length, but not so deeply in this. So yeah, yes. But yes, maybe Pablo has a good intuition on why the effective velocity does not depend on the length of the rod. Yeah, but I don't have a good answer. But yeah, in principle, it's true that it's involved in the dynamics because.
Can I ask a question?
Yes, go ahead, please.
Okay. So yeah, maybe I missed this derivation part, but I wonder how can you show the density function satisfies this PDE, and also if you run okay, so my background is coming from this is I analyze a similar system called ballistic annihilation. So particles are moving with their velocity deterministically, and then when everything when there's a collision, the collided particles disappear. And there was some physics papers that they derived this kind of mean field type for some macroscopic equations that they have to satisfy slightly less rigorously, but the equation gave all the like exact density evolution, and it only recently was rigorously proved in the probability literature. And I wonder, like how can you derive this kind of equation if when everything is interacting on one-dimensional line, not a mean field?
Okay, so I don't know this model that you mentioned, but for the hard rods, the idea so is the following. So you have the macroscopic dynamic UTG.
Mhm.
You prove that, so given in terms of this contraction and dilation operator, you prove that it's equivalent to the one that is written. So maybe you can, yes, maybe you can see my pointer. So you prove that it's exactly equivalent to this. And then from this, you start to compute the time derivative. So so I just substitute my alternative formulation from G, perform, so I call Q hat this inverse of U, where U was here, the position, this guy, and then you compute the time derivative. So, okay, here I know it was fast, but you have some auxiliary results of derivative of each single piece. And then, so here is just the derivative of this product. So derivative of the first one times the second plus your G times derivative of the second one. Then you substitute this quantity that you found independently. And then, so you see here, you are already, so here I think you can put together in this Y derivative, you can put together these two terms. You are here. And basically you immediately see that, you immediately have the PD that you want. So this is the way to find it in this context.
Okay, maybe I'll find more details in your paper.
Yes.
Yeah.
Can you hear me?
Yeah, go ahead, please.
Okay. So I thank you, Chiara, for the talk. Very nice. I like it a lot how you presented. I don't know exactly who asked about the dependency of the effective velocity on R. Okay. So you have an R in the velocity, but it's the incoming R, no, the one associated with the colliding particle, with the target particle, with the quasi-particle, say, that is going at speed v. Because but it so the velocity depends on that, but does not depend on the own. That was your question. In this case, this is the way that the function phi of the collision rate is introduced. I mean.
Yeah, indeed, you're right. Yeah.
Yeah. So for this collision rate, you don't depend on your own size.
That's right. Yeah.
Okay.
But even the effective velocity then.
Neither the effective nor the position. The effective position also at the microscopic level doesn't depend.
Yeah.
So the limit doesn't depend either. Yeah. So the other question, Chiara, was about the limit. How you prove the limit, or how you prove the equation once that you know the limit. The previous. I think
my understanding is the PDE.
How do you derive the PDE?
How do you derive the PDE microscopic?
Wait, maybe I can rephrase the question. So I'm working on other like related type of systems, but there's no particle preservation. I guess in this case, if you collide, then there's some local interaction, but it's more or less the total mass or total size is preserved. There's a swap.
Yes.
Yeah, but for example, like the particles can annihilate each other, or you can start with a bunch of random walks, and then when they meet, they can coalesce into one particle. So in this type of a coalescing type system, is it also possible to derive this kind of like PD equation, or how much does it depend on the details of the hard road system to derive this macroscopic PDE?
No, okay. So in particle system, it's very natural to derive any kind of PD from the underlying microscopic dynamics, even when you don't have conservation of particles.
Mhm.
So for example, it's very common to have boundary reservoir that inject or subtract particle from the system, and then gives you a Cauchy problem with some boundary condition, for example. This is, but okay, so I don't know your particular model, but so this is I would say this is very general.
For example, if we assume two collided road disappears from the system, can we have a similar PDE here?
Probably, yeah. I get it.
Yeah, but then you would have, I don't know, maybe with some peak, some delta, and some complicated, so for sure would be some complicated PDE. I would say macroscopically, but yeah, it would be very interesting to see the effect on the macroscopic evolution of the density of particle.
Well, you can
we
have
can-
this
Sorry,
reaction
sorry,
and diffusion. Yeah, sorry.
Sorry, no, go ahead.
No, I mean that you have some reaction diffusion, for instance, systems that are microscopic, and probably you can do it also with these hard rods that are dynamic, that are deterministic trajectories. Yeah.
Maybe just a comment about the technique. I mean, the mapping that Chiara explained is a mapping to the asymptotic scattering coordinates. So the free particles are actually, the asymptotic coordinates, so they evolve trivially, and the velocities are preserved now and so that this evolution can describe. It's just that this mapping is explicit in the hard rods. It's just a contraction, but like in principle, this is what it is. And in general, it's rather non-trivial. I don't know. So let us thank Chiara again for this very nice talk.